All right, part 3. I told you I'd do this in chunks. So this part right here says fill in the chart. Okay, so you are allowed to use a calculator on this. So if you're not sure what this looks like, you should graph it. But just so you know, a 1/4 means it's really negative 1/2, 4th root of x. So if that gives you any hint, you cannot have negatives under this. So let's see what this looks like. Go to your y equals screen. Turn off your plot if it's on. Oops. By turning off your plot, you press enter. Come back here. I'm going to clear this out. Okay, we have y equals. I'm putting in negative 1/2. Actually, I'm going to put that in parentheses. I don't think you have to, but I just get nervous about fractions. Negative 1/2. There it is. X is right here. X raised to the 1/4 power. 1 divided by 4. Okay. You guys see that? I'm going to press zoom 6 just to make sure I'm on a normal screen. Zoom 6. And that's what my graph looks like. Now, why does the graph look like that? I'm going to press zoom 4. I might press zoom 4. So a square root looks like this. A 4th root just is the same thing, but it's just like skinnier like that. But this is a negative 1/2, so that's why it's like this. It's a negative, so it's a reflection over the x-axis, and it's vertically compressed by 1/2, so it's even closer to the x-axis than it should be. Okay, but that's why it looks like this. So you have to describe some things. First of all, the graph. First of all, it looks like 0, 0, right? Let's look at the t-table. My t-table is messed up. So how do we set our t-table? You press second window. I'm going to start at 0 and go by ones. Make sure that it says auto right here, not ask. That's second window. The screen is second window. Now press second graph. Now I see a 0, 0. I see a 1, negative 1/2. I like that point. 1, negative 1/2 is right there. And let's see what my next nicest point is. Can I just go? Here's one. 16, negative 1. I'm not graphing. Too far. So this is my graph. Okay? Is this even or odd symmetry? It's neither. Even is symmetric to the y-axis. Odd is symmetric to the origin. This isn't symmetric to anything. It's just half of a piece of a graph. What's the domain of this? How far left? It looks like it goes to 0, but it's a bracket. And it goes to infinite, positive infinity forever. Why? How low does this go? Negative infinity, and then how high does it go? To 0, bracket. Oh, I just did the range. Sorry. That's this. I did that one. So that's the domain, and this is the range. Range is low to high. This is left to right. What is the end behavior? You're just describing this. So you would say, as x approaches positive infinity, in other words, as x goes to the right, what is happening to that one end? You would say it's going down forever. So you say f of x approaches negative infinity. As x goes to the right, what is the end doing? It's getting lower and lower and lower and lower. That's what lower and lower and lower and lower means. Does it increase or decrease values? So you read it left to right. As x is going to the right, the y values are decreasing. So the interval for that is it's decreasing from 0 to infinity. You describe the x's. So this watch, what does that mean? As 0 is getting bigger, look, see how this is getting bigger. Look at the y's. What is happening to the y's? They're decreasing. Do you see that? They're getting smaller. The y's get smaller and smaller and smaller and smaller. Slowly, but they are getting smaller. So watch. If you press second window, let's start this instead of 61. Let's go like 6,000. See how the y's are now negative 4? They're getting lower. Slowly, but they are getting lower. That's how you do it. Okay, so let's graph the next one. So the next one is 2. parentheses, negative x, parentheses, cubed. Before I look at this, let's describe this. Does everyone know what a cube looks like? A cube looks like this, usually. But there's a negative inside, so that reflects it over the y-axis. So now it's going to look like this. And it's a vertical stretch of 2. So we should get something that looks like this. So let's look. There you go. Okay. I just want some key points. So let's look at our t-table. I'm going to go second window, start at 0, go by 1s, second window, start your t-table. I'm going to look at these 3 points right here. So we have 0, 0, negative 1, 2, and 1, negative 2. That's the graph I want. Is this even or odd symmetry? It is odd. You can kind of tell in a t-table. Odd means that if you see 1, negative 2, you should see negative 1, positive 2. So whatever order pair you see here, you should see the exact opposite somewhere else. Do you see where this one says 2, negative 16? This one says negative 2, positive 16. And that'll continue forever and ever. So yeah, this one says 3 and negative 54. This one says negative 3 and 54. All your order pairs, x and y, change to their opposite for an odd symmetry. So this one is odd. What is your domain? How far left does this go? How far right does it go? It's negative infinity to positive infinity. Range, how low? Negative infinity. How high? Positive infinity. What's the end behaviors? So as x goes to the right, that's this side. As x goes to the right, what is its end behavior doing? It's going lower, lower, lower. So you'd say f of x approaches negative infinity. Put a line. Now we're going to talk about the left side. As x goes to the left, what is happening to its end behavior? On the left-hand side, the end behavior is going up. So as x goes to negative infinity, that's the same thing as saying on the left-hand side. Sorry, as x goes to negative infinity, it's the same thing as saying on the left side, right here. The y, which is f of x, is approaching positive infinity. Increasing or decreasing intervals. You read these left to right. Always read left to right. Yeah, right here. Make sure you read this left to right. So it looks to me like the y's are going down forever. So you would say it's decreasing for all values of x. If you look at the y values, look at the y's. The y's are going to, like I'm starting right here at 54. Watch what happens to the y's. They get lower and 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 lower. They never come back up. The y's are decreasing for all values of x. Which of these functions have a max of 0? A max of 0 would look something like this. Okay, that's what a max of 0 means. Nothing's higher than the x-axis. So which one of them, you should be able to tell. But if you wanted to graph them, you could just graph all of these. So the first one's negative 3x to the 7th. That's an odd, so it should look like a snake. That does not have a max of 0. So that's not it. The second one is 3x to the 6th. Now this one is even, so it is going to be parabola shape. But it should be going up. So this one should have a min of 0. This has a min of 0. So it's not B, not A. This one, it should be this one. Because it's negative, so it's flipped. It's reflected. So it should go upside down. But any even exponent looks like a upside down parabola. Any even exponent has the end behaviors going the same way. Odds are usually the snake. The odd exponents are the snakes. Do you see that? That has a max of 0. You guys see that? So the answer is C. Describe the increasing or decreasing intervals for this without even punching it in the calculator. This is a reflection of a V, but it's moved 3 right and 2 up. And it's a reflection like this. You can, and this is going to be on the graphing calculator. So if you want to graph this, go right ahead. It's negative. Absolute value is math over to number 1. You can type in x minus 3. Go out of the absolute value and put plus 2. So there it is. The key point is the vertex when describing increasing and decreasing. So you need to know what this vertex is. So I'm writing it 3, 2. When you're describing increasing, decreasing, you just describe with the 3. So you read it left to right. So it's increasing on this side and it's decreasing on this side. So you would say it's increasing when x is less than 3. In other words, it's increasing from negative infinity to 3. That's another way of saying that. It is decreasing when x is greater than 3, or from 3 to infinity. So it's decreasing on this side. You do not use the y-coordinate when describing increasing, decreasing. Even though you're talking about the y's are going up, and then the y's are going down, increasing, decreasing. But you describe them using the x's, the x-coordinate of the vertex. All right, next problem. We're getting our t-tables out. You might want to get the instructions out that I gave you. We are going to make a scatter plot on the calculator and give a rough sketch of what you see. Okay, but before we do that, we're going to punch these in. So I'm going to go, first of all, I'm going to go to y equals. I'm going to clear this out. All right, following your instructions, press stat right here. Stat, then enter, and we're going to bring up our list. Now, I cannot see my list. Oh, there they are. I'm deleting this. So to delete this, go up to list 1, press clear, enter. Over, go up to list 2, press clear, enter. And we're going to enter list 1 right here. The mass and heart rate of a mouse, hamster, rat, Japanese monkey, and all these other animals. So first the mass, how much they weigh. So the mouse, 0.027 kilograms. So we're going to put that in, 0.027. Enter. The hamster, 0.09. The rat, 0.26. Love rats. 6.6, the Japanese monkey. This is in kilograms. 20 is your, let's say, I can't even read that. Something deer. Human, 56 kilograms. And a horse, 494. Wow, that's a lot bigger. Okay, now we're going to go to list 2. This is the heart rate of a mouse. 723 beats a minute. That's kind of fast, huh? Hamster slows down. Rat, even slower because they're a little bit bigger. 147. Heart rate goes down the bigger you are, I guess, right? That's what this is saying. Humans, 80 beats per minute. And a horse, 40. Okay, so make sure these match up. Okay, so we're going to make a scatter plot. To make a scatter plot, see what you see. We got, first of all, mass is my independent variable. So this is the mass in kilograms. This is the heart rate. Mammals, heart rate versus mass, or mass versus heart rate, if you want to title it. All right, so scatter plot, ready? Second, I'll show you what I'm doing. Second, y equals enter. Turn it on. Make sure it says list 1 and list 2. Make sure the scatter plot is on and press zoom 9. So that's what mine looks like. So they're like really close together here. Okay, so it looks like that. You don't have to do any special things other than that. Just kind of show me what your scatter plot looks like. And then, right, what is the linear regression equation for this? So we are going to press stat, go over to calculate, and number 4. So you're going to press stat, calculate, number 4. I said, make sure it says list 1 and list 2. And I'm going to press calculate. I assume I'm going to probably be looking at this in a little bit. So if I want to store my regression, I'm going to go to vars, yvars, function, press enter, and enter. Now I have it in Y1 if I want to see that later. But I want to get down to calculate for this linear regression. So press enter. So my linear regression is y equals negative 0.582x plus 297.075. Come on in. And my R, they're going to, says right here, what is the correlation coefficient? It says it is negative 0.439. So this is very weak. This is a weak correlation. So making predictions off this is not going to be reliable. Okay, so this is a weak correlation. This is my linear regression. Okay, I got that right off of my screen right here. Now, because of the data, if you go back to graph, because the data was not showing a straight line, I'm going to use log-to-log transformations to go back to stat, calculate. Now, to do this, you go up to log 3. And you're going to press log, which is right here, of second 1, and press enter. And it fills in list 3. Then you go up to log 4, and you're going to press log of list 2. Press enter. And then you're going to recalculate to do a new linear regression. So then to do that, you're going to go back to stat, calculate 4. I don't want list 1 and list 2 anymore. I want list 3 and list 4. So I'm going to go list 3 by pressing second 3 and second 4. And I want to calculate that. Now, my new linear regression is y equals negative 0.2, negative 0.269, which is 270x, plus 2.35. But notice the new correlation coefficient. So when you do a log-to-log transformation and it improves your correlation coefficient, see how this was improved? That means that you could have done a power regression from the start. If this improves by a lot, it means that you can have done a power regression from the start. So it says, is the linear regression of the original data better, or is log-to-log regression better? The log-to-log is better. So then it says, use the equation of the regression line of the log-log transform data to write the equation of a power function. Now we're not going to do that, the work for that. We're just going to get rid of all this. We're going to actually just use our calculator to do a power regression. We're going to do a power regression using list 1 and list 2. So because this was good, it means we could have done a power regression of list 1 and list 2 from the beginning. So in other words, when you see something like this and it's really weak, you should just go straight to power regression. It's because it's going to be better. So to do that, we're going to press stat, calculate, go down to power regression, which is right here, A, press enter. Now we want to change back to list 1 and list 2. I'm going to store that by pressing vars, y vars, enter, enter. I'm going to calculate this. This is my power regression. So that is y equals 224.3 x raised to the negative 0.27. Okay, so this is my power regression. Now, if you notice, I just stored that in this. I stored it already. If you haven't stored that yet, just go ahead and type it in. Like just type in 224.3 x raised to the, what was it, negative 0.27. And just press graph because the scatter plot's still on there. And do you see how now it's fitting that perfectly, that original scatter plot? Because that's what a power regression is doing. The reason it's going down is because it's a negative exponent. It had a negative exponent. So it says put this power function in Y1 and predict the heart rate of an elephant with a mass of 3,400 kilograms. So one way you could do this is by doing this and putting 3,400 in for X and do it that way. Or, because I have this graphed in here, I don't care which one you have here, I'll get rid of this one. Okay, let's just get rid of this first one. No, I want to get rid of this one. This is the original one. This has all the decimal places. I can go now to second window and start this at 3,400. You guys see that? And go to the T table by pressing second graph. And it means the heart rate's about 24.999 or about 25 beats per minute. And that would be pretty accurate. So an elephant's so it's very large. An elephant's bigger than a horse. So that 25 should be lower than what a horse's was, which a horse, remember, was 40. So an elephant's going to keep, 3,400 pounds. So we're saying 25. That kind of makes sense to the numbers that we see. Okay, so hopefully you understood that. I'm going to stop this right now because my class just came in, and I will do the next part in a second.